So welcome back, everybody, and welcome to this session on quantum computing and the setup of actual calculations and the variational quantum eigensolver. So I'm going to baby step you guys through the ingredients which you need to encode for project number one. So I wanted to remind you of some of the technicalities which we are going to look at. So let's slowly go through the main messages this week. So we are going to give you a quick reminder on gates, measurements, and 1-qubit systems. And then we are going to look in more detail into the quantum eigensolver algorithm, which is a standard algorithm for solving quantum mechanical problems on quantum computers. Now, we are going to go through the 1-qubit case in some detail. And then when we are done with that, we're going to rewrite the 2-qubit case in terms of Pauli matrices. And the thing which is going to be somewhat delicate is actually how to find the rewriting of the given parts of the Hamiltonian operator in terms of various gates and how we can perform the measurements. And this is essentially what this lecture is about. So let's take a closer look. I'm going to switch between the whiteboard, the Jupyter notebook, and the slides here, back and forth. So for the discussions of a 1-qubit case and 2-qubit case, Hund's book is actually pretty good. And in particular, if you go to section 611, that's where you will find many of the details on the 1-qubit and on the 2-qubit Hamiltonian. Next week, we are going to introduce a Hamiltonian which some of you have met in courses in many-body physics, which is called the Lipkin Hamiltonian. And that's a Hamiltonian which we can rephrase easily in terms of Pauli matrices. And that means that it's really ready for being implemented on a quantum computer. There is a review by Tilly et al., which is the one I've snatched some images from, and I normally recommend taking a look at that. So this is the essential tool for solving many-body type of problems on a quantum computer nowadays. And if you go into a library like Qiskit, you will actually see that Qiskit integrates with a very popular quantum chemistry library, which is called PySCF, where you can set up Hamiltonians and translate these Hamiltonians into Pauli gates without you having to do it. Now, here, we are going to do it ourselves. So we're going through all these painful operations so that you see what is behind the curtains. Now, if we now just do a quick reminder of some of the main gates. So we have the Pauli gates, or the Pauli matrices, which are then represented in terms of X, Y, and Z. And this is just a quick reminder of these 1-qubit gates. And these are related to unitary transformations, which we are making on a system. And sometimes we have often an operator which is just given by a Pauli Z matrix. Then we know that when these act on the computational basis which we have, then we know that the basis 0 and 1, when we act on this with X, this flips the state from 0 to 1, and vice versa. The Pauli Y gate flips the bit and multiplies with a phase by I, which is the same as e to the I of pi. And then we have the Pauli Z gate, which multiplies only the phase of 1 of the 1-qubit state by -1. So these are the states which we have here. And you see now also, just as a quick reminder, that the Pauli Z gate has the computational basis. If we have chosen 0 and 1 as a computational basis, it has these states as eigenstates. Then we have, as a quick reminder again, the famous Hadamard gate, which is also a unitary gate. And in both the whiteboard notes and in the lectures here, I will try to make a distinction between the Hadamard gate, which I write as a plain H, and the Hamiltonian, which will be written like that. So for the symbols, hopefully this works well for everybody. Then we have a famous gate, which is called the S gate, and that multiplies only the phase of the 1 qubit state by just an imaginary component I. So that's another type of rotations, where you then have fixed the angle here to, so there would be an exponential here with an angle of pi times an angle phi. Then we have the inverse of that gate. So these are all unitary operations, and I'm just listing them here just for the sake of completeness. Then finally, we have important gates, the so-called 2 qubit gates. And many of these gates are so-called essential gates. And with, let's say, like a C0 gate and a NOT gate, we can actually perform all types of computations. So these play the same role as universal gates in classical computing, where the NOT gate and the NAND gate are the essential building blocks. And these gates act on the second qubit in this tensor product of 0, 0, 0, 1, 1, 0, and 1, 1. And similarly, we have the swap gate, which actually acts only on the 0, 1 and the 1, 0 state. And this is a typical state which we can make by entangling parts of the state with a Hamiltonian, like we discussed last week. So last week, we looked at this 2 qubit Hamiltonian, where we could switch gradually on the interaction. And then as we switched on the interaction, the lowest lying state of the system switched from a 0, 0 to a mixture of 0, 1 and 1, 0. Yeah? Yes. Yeah. Now, another thing which you will see now is that, and in particular, when we come to the Lipkin model and a more general Hamiltonian, is that a general Hamiltonian is going to be a string of operators. So it could be the identity operator, the Y and the C, etc. Now, one thing which we are going to discuss now in more detail is that when we are going to make a measurement, we will normally make the measurement on only 1 qubit. And I'm coming back to that, why that is the case. So we tend often to order these parts of a Hamiltonian. So a Hamiltonian will be rewritten in terms of strings of Pauli matrices and the identity matrix. And we can now think of one acting on subsystem 0. So that could be the first qubit, the second qubit, the third one, and the fourth one. And it's pretty common then to write these operations from qubit 1 to qubit 4 from left to right. So 0 is qubit 1, etc. So this is one of the things which we are going to play a little bit around with. Now, when we are going to run the simulations, and this is something, so this slide is a little bit dense, but I wanted to give you some of the basic motivations for what is coming. So when you have an initial Hamiltonian, there is an algorithm which was introduced back in the 90s, and that's called the quantum phase estimation algorithm. That is based on you rewriting a quantum or a Fourier expansion in terms of what we will later encounter as a discrete Fourier quantum transformation. So this will be the first step, and this is something which we will discuss after we've done with project 1. And we are going to look at the quantum Fourier transform and also this quantum phase estimation algorithm. And there's a main reason for why that algorithm is not used. So the algorithm has some properties which are not desired in this era now where we typically have noisy intermediate quantum type of computers, quantum computers. So it's a non-hybrid algorithm, but it can also be non-variational. And the length of the circuits where you run the calculations can actually be pretty long. Now, many of the states which we make, like that entangled state we constructed last week, can actually have short lifetimes, which means that if the circuit is too long, we will not be able to run simulations on an actual quantum computer. So theoretically, we can always do that because we don't have a technical hindrance done which resides in the way a quantum computer is made. So that what was introduced back in from 10 years ago, roughly, was the so-called quantum variational eigensolver. And this is normally referred to as a VQE. So this is a hybrid algorithm. So it's a mix between you running computations on a quantum computer and performing parts of the calculations on a classical computer. And the parts of the calculation which is done on a classical computer is the optimization part. So let's take a closer look at it. And we are going to set up some of the calculations which will be needed. So the starting point is the variational theorem. And if you think of you setting up an eigenvalue problem, you solving a matrix eigenvalue problem, this is actually the same as you solving this problem here. And you're optimizing the problem, and you know that this should give you something which is larger or equal to the exact lowest lying states. And that puts a lower bound on the energy. So if you now look at what we are going to do, is that we are going now to parameterize the trial wave function in terms of a qubit on the Bloch sphere, which means that we can represent a qubit as a function of different angles on the Bloch sphere. So that's the ansatz. But we don't know which angles are those which optimize the energy. So if we have m angles representing qubits on the Bloch sphere, so if we have, let's say, 2 qubits, so one of them could have 2 angles when we are rotating it on the Bloch sphere. So that means it has a random position on the Bloch sphere, and we don't know which of these parameters are relevant. If we then have 2 qubits, we would have 4 angles. If we have 3 qubits, we could have 6 angles, and then the number of optimization parameters just increase. So at the heart of this algorithm, there is an optimization. And I will try to step you through these elements because these are the kind of elements you will have to write in the program. So if you think of the expectation value, your system is going to be in a state phi, and we know that these are the parameters. And if we now have n as the eigenstates of H, we know that this relation holds true. These are if n are the eigenstates, then we know that we can expand this set of angles, these parameters, function defined by these parameters, in terms of the orthonormal basis which we have defined. And then that means that the calculation of this quantity is simply then given by the standard expansion, which you have seen probably many, many times. And this applies to any kind of linear expansion. And then we would then simply have, due to the orthogonality of these states, m and n, we then simply get a Kronecker delta, and we have this ratio, this relation here. And I've dropped the denominator, because that would just add a denominator to this equation here. So that means that the optimization problem which we are going to deal with is the one which you see here. So we are going to optimize with respect to these angles, and we want these as a desired solution. So we're going to have an ansatz for the trial wave function. And this ansatz is based on us initializing the system in some states of qubits. And then we rotate each qubit, and then we have a specific ansatz, and then we try to optimize it. So the basic steps which you need in the algorithm is one, to prepare the variational state. And we are going to step through these elements. Then you measure the circuit in various bases. And this is the big problem. So why do we choose a specific basis for making the measurement? So I will come back to why we do that, because that's an important technical issue in many quantum algorithms. So I'm going to step you through some basis sets which you can have, but you will see then that if you have many basis sets for which you can make a measurement, your calculations are just going to be unwieldy. Now, the classical computer then post-processes the measurement data, and then it computes an expectation value. And then you vary these parameters theta according to a classical minimization algorithm. And this could just be your plain gradient descent. And this is one of these algorithms which are implemented in the examples here. But we could also use a more advanced one, which takes into account the second derivative, or the so-called Hessian matrix, and then makes an estimate for that, and that's called Broyden, Fletcher, etc. That's a very famous algorithm for finding the roots of an equation. And in our case, the roots of the equation we are searching is the gradient of the expectation value of the energy with respect to the angles theta. So this loop actually continues till your gradients are 0, which is the ideal case. And when you have that, you have a set of angles, the optimal ones, and they characterize the ground state. And then you have an estimate for the ground state energy. So you would prepare the qubits on a quantum computer. You would perform operations on it, but the optimization part is run classically. And then when you have these, you perform a measurement on the quantum computer. So the figure which you see here is actually one, if you can see it properly, is one which explains to a very large extent how this algorithm functions. So the yellow ones are quantum computing algorithms or subfunctions or whatever you might call them. And now we are initializing the state first. So we could set all qubits to 0, for instance. That's one possibility. Then we perform rotations on each qubit. We can then entangle specific states. So we can have a C0 gate here, and we can continue like that. And then we perform a rotation to a measurement basis, which we are going to discuss in more detail today. And when we have that, we perform a measurement of given Pauli strings. But here we actually feed in from the weighting and the groupings here, the transformations which we are making. Then this is transferred to the optimization part, where we actually calculate these derivatives and set up the gradients. That gives us a parameter update by gradient descent, which is then fed back into the ansatz and state preparation. So we have new angles, and then we repeat, we perform the rotation measurements of Pauli strings, etc., and then back and forth between the quantum computing algorithm and the classical one. So that's the essential recipe of what we are going to implement numerically today. So to have any flexibility, we need to allow for a given parameterization. And the most common approach is to employ these rotation operators given by the Pauli X, Z, and Y matrices, and where we apply chained operations of rotations around the various axes. And we can perform C0 operations, etc., etc. Now we will start with a 1 qubit case, which is very simple. And then we don't need to involve a 2 qubit gate. But you will see that these are going to be needed when we have a more complicated Hamiltonian, which goes beyond the 1 qubit case. So one step at a time. And after the ansatz has been constructed, the Hamiltonian must be applied. And that Hamiltonian has to be written in terms of these Pauli strings. And the reason for that is simply because these Pauli strings are the way we often think of interacting with a given quantum computer with an external probe, which makes the measurement. So a typical probe can be your particles being in a magnetic field. And if the magnetic field is ordered along the z-axis, which is pretty common, so you choose an axis of orientation, then you would typically perform the measurement along the z-axis. And that's why we often want to rewrite the operations of measurement in terms of one specific Pauli matrix. So, and because your experimental setup conditions the way you're actually going to run the measurement. Then, when you make the measurement, you are going to count the number of times you make one observation, let's say bit 0 and bit 1, and you simply count these and divide by the number of measurements. These measurements are typically called shots in the literature. And each polystring requires its own circuit, and where multiple measurement of each string is required. So let's take a closer look at some of these possibilities. So every wave function is actually represented as this state vector. So this is the 0 state, and this is the 1 state. This just represents a random position on the Bloch sphere. And for a random 1-qubit Hamiltonian, a good quantum state preparation circuit should be able to generate all possible states on the Bloch sphere. Then, before the quantum state preparation, your qubit is in the 0 state, which is very common. So the 0 state could be the lowest state of the system, and you know how to prepare your system in its lowest state. So this is everything we do here, even if it sounds a little bit artificial, is very much conditioned by the way you are running an experiment. Typically, you could think of cooling down the system to low temperatures, and then you expect that the system is in its lowest state, or the ground state, or the fundamental state, as we also call it. And that would be qubit 0. So that corresponds to a vertical position of the vector in the Bloch sphere. And then you can rotate it by Rx and Ry, and then you would get a new state phi here. And the rotation corresponds to the rotation in the Bloch sphere around the x-axis and this around the y-axis. And that gives you a general state on the Bloch sphere. And then the gates with parameters, if you have set up, will generate for us the trial wave function. And the two parameters will be in control of the classical computer in its own. Yeah. So this will be for one of them. So this phi, which you see here, that normally disappears when you take expectation values. Yeah, but so right. Sorry. So this is just a general 1-qubit state on the Bloch sphere. But then when you calculate the expectation values of a problem, then this quantity disappears because you have e to the I minus I phi multiplied with e to the I phi. So that disappears, and that's just one for you. So yeah, this phi here is not one of the parameters you vary. So what you vary is actually these two parameters here. Yeah, because that phase factor just disappears in the measurement. And then these two parameters are those which you will control in the classical optimization part. So there's a recipe on how you do that with Qiskit. I'm going to set up the way you can do it yourself, not using Qiskit, but here you can actually see how you can prepare the state using Qiskit with a rotation with Rx and Ry. So one thing which we need to remind ourselves now is that when we are going to rewrite the Hamiltonian, we are normally constrained by the type of measurement basis which we have chosen. And normally you would use 0 and 1 as a computational basis. So that would be the North Pole and the South Pole on the Bloch sphere. Or you can think of that as a z-axis. So that means that we are going to rewrite everything in terms of operation. So this H is the Hadamard gate. The Y gate can be rewritten in terms of a new transformation. And the Z gate is just a C gate, because you can show that this transformation is given by just the identity matrix. So these are quantities which we will come back to. So the thing I wanted to show you now is actually a very simple case. Just a reminder, and this shows you why we have to choose to make the measurement in one basis, because else you're going to go crazy here. So if you think of these polygates, so let's just switch to the whiteboard here. So we're going to stay with a 1-qubit Hamiltonian. And suppose now that the 1-qubit Hamiltonian is a general one. So this is my H, the fancier one. So we have defined a Hamiltonian, which now contains a constant A multiplied with the unit matrix. So that's one of these 2x2 matrices. These are all 2x2 matrices. There's a new constant B multiplied with a poly Z matrix. There's a new constant X multiplied with the Y matrix. So what we want is obviously the expectation value of this quantity, and that is going to be the expectation value of some state psi, and our psi will be a function of the different angles. Now, I could choose now to make the measurement in the basis of the matrix C. So if we do that, if we now think of the basis for matrix C, in that specific case, we could now think when we diagonalize this Hamiltonian, it's a 2x2 Hamiltonian, and this basis is just 0 and 1. So that means that the state, when we diagonalize the Hamiltonian, will be a linear combination of C1 in the C, which are eigenstates of that one, of this C matrix, plus a C2 of 1. Yeah. Yes. So, yes. Yes. So I choose that as a basis now, right? Yeah. So when I take this matrix, this is a 2x2 matrix, I diagonalize it, and I know that I can write that eigenbasis in terms of 0 and 1 as a linear combination. So this would be after my diagonalization, right? So I can make measurements in that specific basis, but I could say that I want to expand it in another basis. So if you remember one of the exercises we had the first week, we could now choose the eigenbasis for the matrix X. So if I do that, then I have to be a little bit more careful because 0 and 1 are not eigenstates of Z, but I would have a linear combination, which then is simply 1 over square root of 2. And then I have 1, 1. That's one of the states. And the other one is something I will label with minus. And that is simply 1 over square root of 2 of 1 and minus 1. So these are eigenstates. So now I could make the measurement, or rather, I could now make the expansion in that basis, right? So that's possible. So when I do that, what I end up with would be, suppose now I make a measurement. You will see now that I would make a measurement. Suppose I just take these ones, but I could actually choose a new basis, the basis which I call I, which is 1 over square root of 2 of 1 times I, and just one which I call minus I, and that is 1 over square root of 2 of 1 of minus I. That's an eigenbasis for Y. So this is an eigenbasis for Y. And you see that immediately, because if I act with X on plus, that gives me just plus 1 times plus. If I act with X on minus 1, that is simply minus 1 of minus. I just use a minus here. And I can do the same on Y. Yeah. Yeah. And then I can do the same here, and I'm just going to stop there because it's not so interesting. That's a plus 1 multiplied with I. So you see now that these new basis states are actually the eigenbasis of these specific linear combinations. Now, if you now look at suppose me now taking psi of z of psi. And suppose I use 0 and 1 as eigenbases. Then you can show that this is nothing but us setting up C1Z complex conjugate with 0 plus C2 complex conjugate with 1. And then I'm taking the expectation value of Z. So this means that I'm simply multiplying with a matrix. So I'm multiplying these quantities with a matrix which looks like this. And this is then multiplied with C1Z times 0 plus C2Z times 1. And these are just vectors, right? So I'm performing just vector matrix multiplications. And if I do that, then what I would get is that this is simply equal to C1 C squared minus C2 squared. Now, what I could do next, I could perform my measurement in the X basis. So suppose now that I take my matrix X, which is a part of the Hamiltonian, but now I use my basis, which I call C1X, and then this is now given by plus, and then I get a C2X with minus. This is my new eigenbasis. But you see that this becomes very clumsy, right? Because for every such operator, I have to find a new basis, which is diagonal in that, which is an eigenbasis of that specific operator. Because at the end, when we are going to make the measurement, this is not going to be very easy to set up. So if I use that one, then this quantity would then simply be C1x squared, if you do the algebra here, times C1, C2x squared. And you would have a similar expression for the y gate. So it means that my final expectation value, if I now look at this C here, this is going to be given when I run many measurements after n measurements. That will be given by what I called n, what I'm going to call n0. I'm just going to call this n0 here. Let me just wipe out this sign here. So this is n0 minus n1 divided by n, where this n0 is just the number of times we hit C1Z, and this one is just the number of times we hit the C2 of Z. Then we could do the same with X and Y. So it means that with X, I could now set up as following expectation value, and where I simply get the number of pluses minus the number of minuses divided by n. So at the end, this is a type of machinery which we are setting up. Now, what you see here is that when this setup here requires in a certain way that we have been able to represent the state either as this linear combination. If I have the Y gate, I would need a I state here and a minus I state. If I have the Z gate, I'm going to use these two basis states. So it becomes very clumsy and unwieldy. In particular also because when we make the measurement, we often just have one type of probe. And this could be a magnetic field which points along the Z-axis. So that means that I would like to have this basis as my eigenbasis for the measurement. And we often choose that also as our computational basis because it's a handy one and it is reflected in the type of physical system which we have available. So I'm going to make some small considerations here which become important for us. And this is something which often is very neglected in the whole field of quantum, in the whole literature on quantum computing. So let's just go back to the notes here, because what you will find in the slides here is essentially the same type of things which I wrote on the whiteboard here. So when we end up with this Hamiltonian here, 2 by 2 Hamiltonian, we need actually to set up the different operations. So this case is pretty straightforward. That has to be 1. But then when I do the the Z gate, this is the type of linear combination which I could get. But my state could now be rewritten in terms of all these linear combinations or combinations of basis states, where the first one are the basis states for poly Z, basis states for poly X, and basis states for poly Y. And just to remind you of, this is just a reminder of what we put on the whiteboard, nothing but that. So you have everything in the slides as well. And then when we perform the calculations, we see that the first presented eigenvectors for each poly operator have these eigenvalues. And then the second eigenvectors for each poly operator has these different eigenvalues here, minus 1. And then these are the quantities which we end up with, having to calculate. Now, if you now move on, so it's the same which we put on the whiteboard. So the above equations require that we can make measurements in the chosen basis sets. This is not always possible. And that's one of the constraints we have to live with. So when you go into different textbooks and look at quantum algorithms, they are normally tuned so that you make the measurement on just one of the qubits, and a qubit in a specific basis. So when we do a measurement, what we often do then is that we perform a transformation of, let's say, a poly X gate in terms of a Hadamard transformation. So in essence, what we do now is the following. So we are looking after some magic matrix, which transforms the operations which we have. So let's say a poly X. So this could be a poly X, some combination of poly matrices. Then this M represents the gate or matrix which performs the measurement. So if you have applied a magnetic field in the Z directions and you're looking at the spin degrees of freedom, it's very common to choose a poly Z gate as this matrix M. And then we need to find a unitary transformation which transforms the other poly matrix, like this poly matrix X, is given by this unitary transformation in terms of the Hadamard matrix. And this is something which we discussed last week, and we show that this is actually the case. So, so that tells us that we are able to estimate these parameters, and hence the expectation value of the poly X matrix, by using a rotation and measure the resulting state in the computational basis. We can do this for the poly Z and the poly Y matrix because we simply have these operations here. Now, before we take a break, I actually wanted to give you some considerations, because this is important. Now, not everything will be discussed here, but the question you may ask now, why do we measure on just one qubit? This sounds very strange, because suppose we have 10 electrons, why don't we measure on all the 10 electrons? Because you know the system is a 10 electron system. So how do we actually perform the measurements? And these type of considerations are actually the considerations which lead to different types of algorithms, because they are, in a deeper way, they are linked to your experimental setup and how you perform experiments on quantum mechanical systems. So in many texts on quantum computing, people simply state, this is the way we do it, but they don't tell you why. And I think it's a little bit important to reflect about these things, because that gives you a deeper understanding on how we actually realize physically many of these experiments. So one thing is the mathematics, the other is actually the physics, which lies behind. So when you think of quantum computing, measurements are typically performed on 1 qubit at a time due to a mix of theory, practical, which means experimental realization, and algorithmic considerations. So many quantum algorithms, such as those for quantum teleportation or error corrections, they require some kind of mid-circuit measurements, and the outcome determines subsequent operations, necessitating sequential measurements to adapt to a circuit dynamically. Then there is some partial information extractions. Algorithms often need only specific qubits. This is the case with Shor's algorithm, which means that a full system measurement is not necessary. So we will not discuss Shor's algorithm in any detail, but this is something which, if you're interested, you will find actually a discussion of that in Hans' book. Then, if you look at quantum mechanics, the measuring a qubit collapses its state. So potentially affecting the entangled qubits, as we discussed a little bit earlier. So sequential measurements allow controlled extraction of information while you manage entanglement. The measurement basis, most algorithms use a computational basis, which we normally think of in terms of qubit 0 and qubit 1. But you are not limited to that. If you think of a harmonic oscillator, you have in principle an infinity of basis states. But we have singled out, for instance, only the 2 lowest lying ones. But instead of qubits, we could have more than 2, and these are normally called qubits. So you can actually make computations with more than just 2 qubits. But the thing is that the measurement basis is constrained very much by this. And joint measurements in entangled bases are possible but require complex setups and are not always needed. Then there is a very important experimental constraint. So if you make a simultaneous measurement, suppose you have laser fields which act on more than just one electron. And this is why it's so important to have systems which you can think of as isolated systems. So when you have that, what you can risk if you make a measurement on more than 2 electrons or 2 qubits is that the measurement can actually risk to disturb the neighboring qubits and to alter their state. And these are things like hardware imperfections, because if you think of 2 electrons which are trapped in harmonic oscillator potentials, if these 2 harmonic oscillator potentials are very close, that means the electrons are very close, and you use an electric field or a laser on these electrons, you can easily influence the other electron. Then that means that the result of your measurement may be unclear. There will be things like cross talk, noise due to imperfections, etc. And then there is also another thing which is extremely delicate in experimental realizations, which is normally forgotten in a discussion in a quantum computing text because you don't need to deal with it. And you will be surprised to see that the readout constraints and the physical implementations of the readout, the controlled part of a system, is extremely delicate. And that's where you have a lot of quantum engineering in order to realize this. And this is where you can say the struggle takes place nowadays, technologically and from an engineering point of view. And this is why many of these algorithms then are just rewritten in terms of you making a measurement on only 1 qubit. So I want you to keep this kind of considerations in mind because they play an important role, and many of them are actually constrained by the experimental equipment which you have. Then there's also qubit reuse. So in error corrections, you would like to reuse some of the qubits. So the conclusion is that while joint measurements are theoretically possible, the dominant practice of measuring 1 qubit at a time stems from algorithmic adaptability, hardware limitations, and the need to minimize quantum state disturbance. And what this approach does is actually it balances efficiency and the constraints of current quantum systems. Now, in a sense, if you have studied, I don't know if you're familiar with Monte Carlo simulations of a system like the Ising model. When you simulate a system, you could actually perform a metropolis test on a state where you have flipped all the spins, or you can flip one spin at a time. The result is essentially the same, but the last case, flipping one spin at a time and performing the famous metropolis test, is the one which is computationally most efficient. So there are many such considerations when you are implementing something. And here, I would say that one of the biggest constraints which we have is the hardware constraint. And that's why what you're going to see now is going to rotate very much around us, taking a string of Pauli matrices and then just transforming them into a specific operation for unitary transformations, where we then can make the measurement in just one of the qubits. So we should take a small break now. I'm going to stop the recording. So welcome back. What we're going to do now is to look at the one qubit system and just have a quick reminder of what we did last week in connection with the simple example which we have in project number 1. So in a certain sense, what I want to do now is to go through the basic ingredients of what you need to program. So we have a Hamiltonian which looks like this. And we decided to simply define the diagonal part, which is the H0, which we often call the non-interacting part. And then we have the interacting part, which is this one, where we have some fixed elements. And in this specific case, we decided that the computational basis is given by 0 and 1. And that's the basis which has H0 as a actually, H0 has this basis as an eigenbasis. And then we could rewrite with some manipulations the 2x2 matrix in terms of a Pauli Z and a Pauli X matrix and an identity matrix. And that's the quantity we now want to set up a quantum computation of, a simulation using the Variational Quantum Eigensolver. So here I just put up the parameters, and we are now going to look at the code a little bit. So I'm going to switch to the Jupyter notebook now. So let's do that. So let's just scroll down till we hit the target, which is this simple Hamiltonian now. Let's just set that up. So what I'm doing now is just choosing these parameters. And now I'm just diagonalizing with a plain eigenvalue solver. So this is the linalg eigenvalue solver in Python. And that gives us the reference energy with those parameters. And we can then run this in another way, where we now, as you can see here, I define the Pauli X, Y, and Z matrices. We did this 3 weeks ago. And we can then rewrite everything in terms of those matrices. And you see now that the Hamiltonian is defined as this constants times the identity matrix plus a new constant times the Z matrix times the X matrix. So this is just us rewriting the Hamiltonian and preparing it for quantum computations. And you will see that the two eigenvalues are exactly the same. Now, what we are going to do now is to implement the VQE ansatz for that specific simple case. And now, just keep in mind, if we just scroll back a little bit, is that we have taken these Pauli matrices. So we are going to rewrite the Pauli X in terms of a Pauli Z times the Hadamard matrices. We don't have a Pauli Y matrix, so we don't need to worry about that one. But these are the eigenvalues. So we are now going to make these computations, and these are the transformations which we're going to make. So this is the rotation around an angle theta, and this is the rotation around an angle phi. And what I do here, as you can see, this is, as we discussed a little bit earlier, so this is just a reminder of what we did. This is a pretty stupid calculation because I'm just fixing two angles. I don't know whether these are the optimal angles or not. So there's no optimization here. And you can see now I implement Rx and Ry. And then I have my basis, the original one, basis 1 and basis 0. The new basis is now simply the transformed basis, where I fix now everything as a qubit 0. And then what I do next is I perform now the calculation with this basis here. And I have the same Hamiltonian as before. So I'm not making a measurement. I'm now just making a plain computation. So there is no me rewriting in terms of a Pauli Z matrix, the Pauli X matrix. Okay? So this is just a straightforward implementation of the calculational recipes, where I now take the new basis. So I'm just skipping the quantum computing measurement part. And you see here that the eigenvalue, which I get with this specific choice, is actually not the best one. So if you print the energy here, it has an energy of 2, and it has an imaginary component as well. So this is 2, and I should actually have 0.98. So this is not very, how to say, this is not exactly what I'm looking after. So I could do the next thing without making a measurement and not preparing this as I should have done. I'm simply just taking the basis, and you see now I'm performing the operations here, and I choose a set of random values for these angles. So I just give it a random value here in a range, and then I run the calculations. And then there is one specific value which gives an expectation value, which differs only with the true one with at the order of the second digit after the decimal point. So this is the difference between or actually the minimum difference between the exact one and the one which I compute in this brute force way. So as I say, this is not the way you will proceed. And one thing which we need to do is actually to calculate the gradients, because now we are going to implement a gradient descent. And I assume that everybody here is familiar with a gradient descent method. Before we do that, what I wanted to remind you of is the following. So let's just go back to the whiteboard. So what we have done now is to take an initial state, which we prepare. So this is a 1 qubit system, and this initial state is just given as a qubit 0. And then we are now obtaining a new state, psi prime, and this is going to be given by a rotation around an angle phi, and then the rotation around an angle theta times 0. And we would typically then rewrite that in terms of qubit 0, and then there is an Rx. So the first one is the one to the right, and then we have an Ry of phi, and then we end up in a new state. Let's just call it psi here. So this is our variational ansatz, and we have now prepared the system. If we now look at the X state, or the X matrix, this is something which we could rewrite now in terms of a Pauli X with a Hadamard. And then we would create a state prime, which is given by the Hadamard gate, H. So this is not the Hamiltonian, acting on Ri of phi, of Rx of theta on 0. So that's our new state. Now, it's common in the literature now. So what I have here is just the state which is being manipulated by unitary transformations. So in principle, what I'm doing here is just a series of unitary transformation, which I can call U1 times U2. And in principle, I could actually have many such transformations acting on an initial state. So this is in principle what I'm doing. So these Rx and Rys, etc., They are just unitary transformations of our state. And this is then the Hadamard, which is also a unitary transformation. So when we look at these calculations which we want to do, so we have a Hamiltonian which contains a term A times I, the identity matrix, plus a term B, and then I have my state psi, and then I have my Z matrix of psi, plus this C, sorry. I'm just testing my knowledge of the alphabet. So if you look at these quantities, this is something which I would rewrite in terms of an A, and this I is just equal to, we don't need to do anything here because that's just going to be 1, plus B, and then we have this state which we have transformed, but then the second term is now going to be equal to a psi prime times Z times a psi prime. And then we know that the Pauli X gate is given by 2 Hadamards times Z times H. And then we have the state psi, which is simply given by Hadamard times Ry, and I skip the angles here, times Rx times 0. So it's common then, when we now are setting up the measurements, to actually measure or calculate or evaluate these individually. So what it means is that we need, if we now skip the first one, the way we often write this, the psi of Z of psi, is something which we write as a 0 for the 1 qubit case. And then we have the Rx, and then we have the Ry. Then I'm going to put a dot here to indicate that now comes the final operation where we are going to make the measurement. So we're going to make the measurement in the C basis. So pay attention to the drawing which we made here, where we now are just indicating that we got a new state. Now let me just cancel this one because I don't want to. So the states which we have here, this is not the same as the kind of graph which we made here, where we now are indicating that we have this expectation value we want to calculate. The state is prepared in a 0 state, and then we perform the rotations, and then we make a measurement. Similarly, if I look at the next case, where I have phi with x phi, this is something which we will indicate with a 0. This is now transformed via Pauli X operation, or Pauli Y. And then we now have a new gate here, an H. And then finally, we perform the measurement. So there's a distinction between the two in the fact that we now perform a Hadamard operation. And this is the same as us setting up a psi prime of Z, where we perform the measurement of psi prime. And this is the same as psi with a Hadamard transformation of Z of Hadamard acting on Z. So these are all kind of equivalent notations. And if we have a Pauli Y gate, then which we are going to perform the measurement on, then we have to introduce this phase matrix. So suppose now that we, for the sake of completeness, also look at this one, psi, then we know that this gate here is actually given by H acting on the Hermitian conjugate of Z, and then I have H times S. So what that means is that we are going to make transformations of this type. So where we have the state 0, which now goes into, is transformed by a Pauli X, and then a new rotation. And now I have my S matrix, and then I have my H matrix. And finally, I am performing a measurement now in my chosen computational basis. So this is a way by which you would indicate that specific operation. Okay. So let's now go back to the Jupyter notebook and look at how we now would implement this. Using the Variational Quantum Eigensolver. Now, I'm going to go through these technicalities using the Jupyter notebook because we need an expression for the derivatives. And the nice thing now is that we can actually, with these rotation matrices, we can find a very compact and nice analytical expression for the gradients. And this is the kind of expression which we end up implementing. So what I want you to think a little bit of now are the expressions which follow. And you will see now if I take one of these rotation matrices, which are given by this expression here, then we know that, so I here, this is the imaginary I. Then this is given by the identity matrix. We have this angle, gamma half, and this is then multiplied with the appropriate Pauli matrix, which can be sigma x, sigma y, sigma z. When we are calculating the derivatives, so keep in mind now that we need to take the derivative with respect to these angles, because this is the problem we want to optimize. What we need now is this expectation value, which you see here. So when I calculate this expectation value, I'm going to calculate the derivative with respect to the angle theta and with respect to the angle phi. So the complication now, if you have more than one qubit, is that you will have more than just two angles. So you will have many angles to deal with. So normally twice as many as you have qubits. And then what you see here is that when you take the derivative with respect to phi, obviously that targets the sigma y. And if you do the derivative with respect to theta, that targets the sigma x. So you will have the first expression plus its Hermitian conjugate. Okay? Everything okay? So what we get then, so when we do this, we will actually, and this is other derivations which follow now, this is the compact expression which we can encode for the type of transformations which we are making. So that means that your derivative of the Hamiltonian, the expectation value of the energy, is given by the Hamiltonian plus an angle pi half minus an expression with the same angle minus pi half. So this is something which can be efficiently calculated, because you remember that if you're doing machine learning, and I know that you guys are familiar with that, then the calculation of the derivatives is often something which is very complicated. So for our case, with this variational ansatz, with the rotation angles, we have straightforward expressions which are analytical ones and which can be evaluated quickly. And this means, if you now look at these calculations here, what we need is simply to consider these matrices here, which are given by these rotation operations. And if you now look at the derivatives, where the sigmas can be any of the Pauli X, Y, Z matrices, these derivatives are actually equal to this quantity here. And then we know that when we use the block sphere, suppose now that we just look at one angle, just for simplicity. Then we know that if we have only one angle, the expectation value of the Hamiltonian is simply given by this quantity which you see here. And when I then take the derivative, I have to take the derivative with respect to this angle dependence and this angle dependence. So H, the original one, does not depend on any angle. There's no angle dependence there. The angle dependence comes in the rotation matrices. So when you take the derivative, what you have is simply an expression which looks like this, plus its Hermitian conjugate, because you're taking the derivative here as well. And that will just give you, since this is a Hermitian conjugate, that will just give you a plus I here. So when I say Hermitian conjugate, that is just you taking the derivative with respect to this term and the second term. So I hope you don't get offended if I remind you about the chain rule. Then there is an expression which is very handy. So if I have because you see now that your expectation value is something which involves three operators. So you can rewrite them as operators A, B, and C, where this one is just the Hermitian conjugate of C. And this is the expression which you then get. And A, B, and C, in this case, are arbitrary Hermitian operators. But in our case, A is equal to the identity matrix, and with B being equal to the Hamiltonian, and C is simply equal to this specific Pauli matrix. And if you do that, then you can show that this expression which you have is nothing but this one. And where we use that, the rotation matrices can be written like this. And with an angle phi equal pi half, this corresponds to this expression. And if you do that, you can actually rewrite this like this, which is the same as two distinct expectation values. This is the expression which is encoded in the programs here. So when we are computing the quantum gradients here, if we now go back to the same code, what I've done now is to perform a brute force gradient descent. So it's the same Hamiltonian. I perform a classical diagonalization. And now what I'm doing is simply to set up the Pauli X, Y, and Z matrices. I am performing my rotations, Rx and Ry, around angles. I defined my expectation value of the energy in terms of these angles. So that's a function, which then is going to be used when I calculate the gradients as well. So everything here is done manually, as you can see. There is no automatic differentiation, no nothing. And here I set up 100 iterations and a brute force gradient descent with an parameter, so-called learning rate, 0.1. And now I calculate the gradients. So I'm simply using that expression with theta of plus pi half minus pi half. This is the other gradient, since I have only one qubit. So I have only two angles. If not, I have to rewrite this in terms of an array which contains all the angles which I have. So I'm evaluating this one exactly. I set up my update rule. And you see now when I run it, this is what I get. This is the exact value. And by this recipe now, when I print the energy as a function of theta and phi here, I'm actually getting an imaginary contribution, which is essentially 0, 10 to the minus 21, and a real part, which is almost equal to actually to the 1, 2, 3, 4, 5, 6, 7, 8, to the 8th digit after the decimal point. Yeah.
Such as well, so we can take that.
Yeah.
Because of the imaginary.
Exactly. Remember now that I've been playing around with a learning rate here. So in a way, I've been cheating you a little bit, because if I were to do that, I may not get these nice results. So you see, in this case, I'm getting this as a result. So you would actually tune the learning rate as you would do in any optimization path. Now, in the code below, you will see how you can use one of these algorithms, which you find in SciPy, which is called Broyden's algorithm, for actually driving the gradients to 0 with very few iterations. So what this means is that if you look at what we have done now, is also that we are setting up several matrix and matrix vector multiplications. And although this is straightforward, it is not the most efficient way of doing that. in physical realizations of this system, we cannot just multiply the state with the Hamiltonian. And when performing a measurement, we can only measure in one particular direction. So keep in mind that this code here just sets up the whole Hamiltonian matrix without thinking about making a measurement. And this is a crucial part which comes now. So the smarter way of doing this is actually to rewrite everything in terms of these Pauli C matrices and make the measurements in just that basis. So the code which follows here is actually, in a way, it's a kind of my solution to project one, that specific part. So take a look at it, because this is the way you would actually envision the solution of the 2-qubit problem, but also the way you would solve this more advanced Hamiltonian, which we are going to discuss next week. So that you have essentially different types of Hamiltonians, which we are going to study computationally. And that's essentially project number one. So that you see all the different steps here. And now what you will see is that here I am writing the Hamiltonian as before. There is no change. It's exactly the same. There is a classical eigenvalue solver. So this is just us called lin eig. As you can see here, nothing changes here. And then I'm plotting it, and this is what you see. This is also an example of a so-called level crossing. So when I switch us this interaction, this state is 0, this state is 1, and this becomes state 0. So that's a quantum mechanical level crossing where the states change character. So as I said, this is a standard eigenvalue problem. Now I'm setting up my preparation of the state. So you can see now I have my theta, phi, the target value. So I'm performing the Rx and Ry rotations with the angles as before, except that in the previous case, I was setting up the full Hamiltonian without thinking of me making a measurement in a specific basis. Now in here, what I'm doing now is I'm calculating the expected value of Z. And now you can see the expectation value of Z is omega plus these parameters. And now I calculate the number of shots, the number of experiments I'm doing, minus the measure divided by the number of shots. But then here, I'm now setting up the same thing, but I'm recalculating this one in terms of the Hadamard transformation. So my measure X is actually something where I actually take the qubit state, but I apply the Hadamard to it. So my C case is simpler, whereas my X case now needs the Hadamard to make the transformation. So this is the setup of the Hamiltonian here. So let's just rerun it here. So we have, sometimes it's always when you run Python, if you rerun only one of it, it doesn't. So there is also a function which you will find in the folder, which is called QC, which contains the setup of a 1-qubit state and a 2-qubit state and other functionalities, which we will discuss in more detail next week as well. So here I'm just setting up the minimization, and this is my own minimization where I now set up the angles. So I take plus pi half, minus pi half. So I have a E plus and E minus. So this is my energy here. And then I get the, I have a learning rate, and then I have a learning rate times the gradient here. So if I run this one, so let's do that. Then I'm using SciPy, the optimization function. And in this specific case, what I'm doing now is to use Powell's method. You can use Broyden's method, and then you would have BFGS as an option here. So this one, if we now rerun that, and then make a plot at the end. So now we are actually performing the measurements by a given number of shots, which in my case is 10,000. And then you see the final result for the ground state here. So this is the optimization with scientific Python. This is my brute force with a plain gradient descent. So this SciPy method does normally a better job. And I would recommend using that one in project number 1 when you're setting up your own code. And you see here the basic result is that you get a pretty good agreement. You have some outliers from my own code, but that is because I need to tune the learning rate, which I did not do here. So I would recommend, if you look at the recipe here, where I simply run in a very brute force way over the set of the gradients, I would not recommend doing that. Yeah.
So in this case, we have the answer
Yeah.
we're looking for.
Yeah.
So that's why you code rates.
Yeah.
How do you optimize this when you don't actually know the answer?
Then you have to think, if you do a stochastic gradient descent, you would have to set up an array of learning rates. And you could also think of, if you're familiar with it, I don't know if everybody's familiar with machine learning, but in machine learning, if you do a stochastic gradient descent, you could have an optimizer like Adam, root mean square propagation, or any of these methods to update your learning rate.
Yeah. Machine learning as well, you already have the answer because you know what the answer of something should be.
Yeah.
But in like you have a many-byte system, and you don't know the energies. You
would pick the calculation which gives you the lowest energy, because you're using a variational calculation. So that means that for those learning rates and those angles you get, you have the best energy. So if you don't know the answer, that's the way you would do it. And the other thing you would do afterwards as a post-treatment is to calculate the variance, the expectation value of the variance. Because the variance itself, if you have the exact solution, the variance is equal to 0 for Hamiltonian system. Because the variance then, and you can see that immediately. So when you make this type of optimizations, so many people mix the optimization with respect to the energy and with respect to the variance. Because if you don't know the energy, one thing you know is that if you have the exact y function, the variance is exactly equal to 0. And you can see that if you now calculate. So this is a very important point. So how do I know that my results are good ones? So let's just remind ourselves a little bit about that. And we switch to the whiteboard. So if you now look at the variance, so we have calculated the expectation value of the energy. So formally, the expectation value of the energy is now given as, so we typically write it like this. So this is our Hamiltonian. And then we have an integral or calculation of psi of h. This is actually h of psi. And we get something in principle which should be equal to or larger than the exact lowest lying energy. This is the variational principle, which is used in the variational quantum eigensolver. Now, if I calculate the expectation value of this quantity here is obviously psi of h acting twice on psi. Now, if h times psi is equal to the energy which we are looking after, if that is the case, you know that then then this is nothing but the energy squared. Now, the variance of h is nothing but the expectation value of h squared minus h squared. That's the mean value. That's the variance of the energy. And if we now have the exact solution, then this is identical to 0. Now, to calculate the variance is more involved. because you would in that case have to evaluate h squared. So we want to avoid that one because that involves many more manipulations. But what you would do then, when you find the lowest energy with a given combinations of angles, then you can calculate the variance at the end of the calculations. So some people vary both the variance and the energy as a function of the parameters, because you know that you have an exact bound, an exact value for the variance if you have the exact wave function. But this would be a typically in order to save cycles, you would run this as a post-calculation evaluation. Okay? So that's one of the ways by which you would run the calculations here. Now, this was the 1 qubit case. Now we are going to go over to the 2 qubit case. So if we now look at the 2 qubit case, we have a Hamiltonian now, which we are going to rewrite. So let me just write this one down. There is a simple Hamiltonian, which we looked at last week as well. And in that case, we have a Hamiltonian which looks like this. So there is some epsilon 0, epsilon 1. These are the diagonal cases, epsilon 3. And here we have a plus, an HZ. There's a 0. There is an HX. There is an HX here and a 0. This has a minus HC. There is a minus HZ. And there's a plus HC. There's a 0 here, a 0. And then here we have an HX and an HX, 0 and 0. And 0 here. That's the Hamiltonian which we have. This is something which I can rewrite in terms of different combinations of Pauli matrices. So I can write this out as an unperturbed part or non-interacting piece, H0, plus an H interaction. So H0 is now going to be given by this epsilon 0, epsilon 1, epsilon 2, and epsilon 3 of 0. And H0 has as a computational basis these eigenvalues and eigenstates. And then I have an H0, 0, 1, which is epsilon 1 of 0, 1. And then I have an H0, 1, 0, which is epsilon 2 times 1, 0. And then I have an epsilon 0 of 1, 1, which is an epsilon 3 of 1, 1. Now, the interacting piece, this H of I, is something which we can write in terms of Pauli X and Pauli Z matrices. So this H of I is simply going to be given by this H of X. Oops. And then I have a Pauli X tensor product with a Pauli X plus an HC of a Pauli C times a Pauli C. So a Pauli C times a Pauli C is nothing but 1 minus 1, 0, 0, 0, 0, and 1 minus 1, 0, 0. And the Pauli X tensor product with Pauli X is actually nothing but 0, Pauli X, and this is a 2 by 2, 2 by 2, and 0. Now, I want to make the calculations in a given computational basis. And now I have to perform transformations. So if you now think of this as just as a chain of Pauli matrices, so we could think of this as a quantity P, and I want to find a unitary transformation for this specific chain P, where I have now M, which is my measurement basis. So think back to the example with Pauli X, which was given by a Hadamard times Pauli Z times a Hadamard. Okay? Now, I want this here to be the Pauli Z matrix. This is where I want to perform my measurement. So I have to make transformations of the different types of operators. I have to transform that one. I need to transform that one. So there are specific operations which we can make, and we will look at closer at that next week. But I want to show you what kind of transformations we now need to make by just going back to the Jupyter notebook. And this is the last thing we're going to do today. And I want you to look at this till next week, because then we're also going to set up the code for doing that. And then we are going to move to a slightly more complicated Hamiltonian. So this is what we have. So we have these terms here. There should actually be V of X here. Sorry, I didn't see that before now. What I'm going to do now is to rewrite the diagonal terms, and you can show that this is equivalent to what you did with the 2 by 2 matrix. I can rewrite the diagonal term in terms of this combination of matrices. And keep in mind now, this applies to the first qubit, this to the second, first qubit, second. So this case is pretty simple because we are going to make the measurement in the basis of the first qubit. And you will see that next week when we break this down in terms of the computational basis which we have. But then we need to change this one to a C basis in the first qubit. This is a C times C, and then we have C tensor product C and V of X tensor product XX. So how do we perform the measurements? So we want to perform this operation here in the basis of the first qubit. So what we need then is actually to make transformations of this type here. So this is already as we want to have it. Nothing happens with qubit 2. We perform the measurement in the basis of qubit 1. But then this one has to be changed. And next week, we are going to set up all the expressions which are needed. So I just want you now to show that if you take these definitions of these matrices and perform these operations, where M is just a Pauli Z gate, if you do that, you will get a Pauli C gate set of operations where C is applied to the first qubit only. So here C is applied to the second qubit. We can transform that one by a swap gate. So if you take a swap gate and multiply that with C dot I and multiply with a swap gate and take the difference between that and this equation here, you should get 0. So we are going to play around a little bit with that next week. But the problem now is that when you get into more and more complicated systems with more and more qubits, we need to make these transformations in order to be able to make a measurement in a given basis. So this is the kind of complication you get when you do quantum computing, because you want to relate what you're doing to a specific experimental setup, which then constrains your operations. So typically, most quantum algorithms are based on you making an operation on only one of the qubits. That means that we have to set up more complicated circuits and operations in order to perform the final evaluation. So for the 1 qubit case, it was simple because we had just an X gate and a Z gate, and we could make a simple transformation of the X gate into a Pauli Z gate by a Hadamard transformation, but now we need to go through these different types of operations. So next week, I will discuss this in more detail in the first lecture, and then we are going to look at how we can perform the calculations much along the same way as we did for the 1 qubit case here. But we need to set up the Hamiltonian in this basis of Pauli X and Y and C matrices. And then when we're done with that, we are going to introduce the final Hamiltonian, which is going to be this Lipkin Hamiltonian. So that will be towards the end of next lecture next week. And when we're done with that, the week thereafter, then we will look at how we encode this properly. So then you should have everything which is relevant for project one. So life gets more complicated when we move away from the cozy 1 qubit case. But I hope you see the overarching message. We break everything down into a basic gate and a computational basis, and we make the measurements in that computational basis.